Hello, welcome to Scalable CTO. I'm Bob Dickinson. Today we're going to talk about GCP Databases, specifically Cloud Firestore versus Spanner. So let's talk about what the two databases are. First of all, you have Cloud Firestore. Google talks about that being ideal for mobile and web apps, requiring real-time updates, user-specific data, common in apps with rapidly changing data. It's basically a document database that stores JSON documents and can access them via indexes very quickly. So it's sort of a database. You can definitely use it like a database. It has its own query language. It has atomic field level operations, which I'll talk about in a little bit, and batch writes and sort of transaction support, although you might not end up needing them. And it's truly fully managed zero ops. It just always works. You stand it up, you call its APIs to get and put data, it scales, it's fast, it just works. There's no configuration management, anything. It's just an always on document store database. So Spanner on the other side, they talk about that being best suited for enterprise apps. It provides strong consistency, which is one of its big differentiators, global transactions, does complex queries across large data sets. They talk about financial systems, large scale analytics. So it sort of sounds like this is a database you want to use for, enterprise backend kind of stuff, not something you might use for like a consumer social network app. So it didn't really seem like the right fit at first. But we changed our mind about that after getting into it a little more. So it's a SQL database. It supports SQL queries, joins, aggregations, full ACID transactions. They say it's fully managed, which it sort of is. It's not zero ops. I mean, it's still a SQL database, so you're still going to have all of the issues you have with any SQL database and how you have to manage and optimize and tune it. But there's a little bit of work there, and I'll talk about some of that as well, that makes it not quite as nice of an out-of-box solution, especially for a startup or a new app. So we switched. We started with Firestore and we went to Spanner. And I sort of like the Hemingway quote, "How did you realize you went bankrupt?" From The Sun Also Rises. And the answer is two ways, gradually, then suddenly. I feel like that's kind of what happened with the database. We started using Firestore. It was great. And then we just started, we kept bumping our heads into things where it's like, that's not great, or we had to do a little bit of workaround to make this work, or there's some limitations, and we'll kind of figure that out later. And just the weight of it built up over time to the point where it kind of became obvious that we picked the wrong database. So as I said, we started with Cloud Firestore. It really seems like the way Google markets it, and with the tooling around it and sample apps, like it just seems like, this is what we want. It's going to be quick and easy. But as I said, we built our app and we started running into more and more limitations. Spanner, on the other hand, is marketed the exact opposite way. They're sort of trying to sell that to for enterprise backend OLAP, whatever data analysis kind of apps. But it's just a SQL database, right? It's like Aurora on AWS. It's fast, it's scalable, it's relatively easy to manage, and it's SQL, which so we know we're not going to have any kind of limitations on what we can do. So we migrated to Spanner, and I'm going to talk about sort of more of the details of why, and then also how we did that. And I will say that after going to Spanner, I'm very happy with that choice. It was definitely worth the time and effort. I wish I would have started with Spanner. And hopefully I'll give you enough information that if you're in a similar situation, if you're using one of these databases or you're thinking about picking between them, that you'll be able to make a better choice. You might not pick Spanner, but you might at least be able to make a more informed choice and make sure you pick the database that's going to work best for you. So I'll talk about our use case, what our app is, and our tooling, just so you sort of understand our perspective on how we use the database. And then I'll go into our Firestore implementation, how we use it, the limitations we found, and why we switched. And then into Spanner, similarly, sort of how we use that, some of the tooling and techniques we use to make Spanner work well for us. I'll point out some key differences between the two, and then I'll go through how we actually did the port from one to the other, which is if you're contemplating something like that might be interesting, and then a little bit of summary at the end. So to start out, let's talk about our use case with TeamSpark. So we have a real app that we implemented initially with Firestore and now with Spanner. It's not a giant app, but it is a full real app. It's 35,000 lines of code between the mobile client and the API server. It's 12 data models that we make available to the app layer. It's 260 plus integration tests, which are at the API server level, and they hit the models on production DB infrastructure. So the integration tests run directly on Firestore or Spanner in production. And we did a factory pattern that allows us to switch between the database implementations by configuration. So we can basically run it in a mode that uses Firestore and in a mode that uses Spanner, either or side by side. That probably won't last forever, because at some point as we start to get around some of these limitations in Firestore, we're going to start changing the model in ways that Firestore can't support. But for right now, They're running side by side. So in Firestore, we have 10 collections, 42 indexes, and it's about 3,500 lines of code for the implementation. Spanner is 22 tables, so a little more normalized. It's got 20 indexes. If you counted the primary keys on Spanner, it's 42, so it's basically the same number of indexes, and about 4,250 lines of code. So a pretty similar amount of code to implement both of them. And they're both implemented using the Node.js libraries from Google for the respective platforms. So what is the app? I'm not going to go into a lot of detail. There's plenty of previous podcasts where I go into this and more, but it's essentially a social networking app that has all the functionality that you might think of something like Facebook having. It's oriented around team and group interaction, so it's not about sort of influencers and followers. It's about groups of people getting together. But there are posts on timelines. You can have comments, reactions to those posts and comments. You can have mentions and hashtags, and there's also a full messaging app with like typing status, notification, all that sort of stuff. So it's a pretty full-fledged social networking app. Our tooling is that the client apps are in Flutter and Dart for iOS and Android. We use Next.js, which is sort of a flavor of Node.js for all of our web technology. So that's the website, the web client app, and our API server. The database is now Cloud Spanner and Google Cloud Storage for media. Our day-to-day development environment is Visual Studio Code and Copilot, and also some Xcode and Android Studio for mobile apps. And we use GitHub for source control and for CI/CD with GitHub Actions. Again, really briefly, we're trying to build a system that will scale to many millions of users. It's highly available. That's relatively inexpensive to run and operate. In order to do that, we have to rely on fully managed services, or as managed as possible, things that are highly available, hyper-scalable, auto-scalable. We want the system to be essentially zero ops, the entire system to be zero ops, so fully automated. So no batch or cron jobs, queues, orchestration that we have to do manually, any scaling that we have to do manually, or capacity management. We want something that just always works, always scales. There's no place to spin, nothing to monitor, no logs to look at, and basically something that never pages me. I didn't start a new company because I wanted to be, an operator on call on PagerDuty and, be putting out fires all the time. So we're really trying to architect a system that doesn't require that level of support. And to do that, we have a strong bias towards what I'm calling zero ops cloud services. So these are like cloud services that just work. So it's just something as a service that just works. So these are things with minimal configuration. You just create an instance, start it up, and start using it. There's no operational tasks. Not only do you not have to do these tasks, you can't actually do them. They just don't exist. So no provisioning, scaling, capacity management, deciding what regions you want things in and how you want to patch and scale and monitor. None of that. Ideally priced based on usage, and usage can be defined in a lot of different ways. It might be storage, it might be data transfer, or something like that, but it's something that scales to your usage. It's a scaled platform that's consistently and predictably high performance, available everywhere, every region, whenever you need it. And examples of these kind of services are things like Amazon S3, Google Cloud Storage, and Cloud Firestore, for example. They're just super simple, no administration required kind of services. And I'm pointing that out because Spanner is not exactly that. Our architecture is we have these Flutter clients, and the web client operates in the same way. They talk to Auth0. That's definitely one of the zero ops kind of platforms, authentication as a service. And then they talk to an API endpoint. The clients don't actually know they're talking to this enterprise or external application load balancer in Google Cloud, but it presents the API, which they call, that takes advantage of Cloud Armor and Cloud CDN pretty automatically. It has API gateway, which we don't currently use, but we have there if we need it. And then that goes to our Cloud Run Next.js instance, which talks to Cloud Storage and to Spanner. So the basic point I want to make with this, and there's a lot more detail in this and other episodes of the podcast, is just these are all inside GCP, and they're all pretty much zero ops, auto scale, magically work, no administration required kind of services. Spanner's not exactly there, but the rest of it is. So let's talk about Cloud Firestore. First of all, there's a couple different ways you can use Cloud Firestore. The way that it was sort of designed to be used, and it's kind of its sweet spot use case, is this idea where you have mobile apps that are talking directly to the database. The user is authenticating as themselves. They're getting security applied as that user, and they're talking directly to the database. So there's no API server, database server, anything in between. It's just a cloud app talking directly to the database, just reading and writing directly to and from the database. And actually beyond that, this notion of real-time data change notifications and offline access. So you can talk to a local copy of your database and have it synchronized later when you get reconnected. It's very tightly coupled cloud application to database. And if you need that, then Cloud Firestore is sort of the only game in town, and you should use that, and that should sort of be the end of the discussion. To me, I've built enough applications, mobile apps and SaaS apps, and scaled them that I'm just really, skeptical about how you would do database migrations, as your data changes over time and the layout changes over time, how you're going to manage that, particularly given that you don't have a lot of control over the code that the client's running on the mobile device. So with the SaaS service, you're sort of serving the code and the data at the same time, so you have a little more flexibility. But with a mobile device where you push that code out through an app store and don't have any control over when the user upgrades it, it just seems very risky. So I've seen this work great for demos and quick and dirty apps and internal tool kind of apps, but I'm just skeptical that model would work for a real legitimate scaled mobile app. So our usage is sort of the other way you can use Cloud Firestore, which is that we use the admin API from our API server to call the database as an admin user. So we apply our own authentication and user-based security and access controls at the API server, and we just call the database as a database. The other thing to understand about Cloud Firestore is it's all about indexes. So everything it does is fast, which is great, and scales. You don't have to worry about that. But everything you do, literally every way that you access data, every way that you filter, sort, select data requires an index in order to do it. That Cloud Firestore literally cannot access the tables of the data. It can only access them through the indexes that you build for it. So in Firestore, an index is not like it would be in a SQL database where it's sort of a way that you can speed up a query and make it smarter and faster. It's literally the only way that you can access data. So that's something important to understand about Cloud Firestore and how they use indexes. I will say that it does automatically create indexes on every individual field, but those are almost never useful unless you're just getting like a record by ID where you're selecting a single record or by a single piece of data. But if you're searching or sorting that in any way or adding any other filtering, those default indexes are, at least in our case, never used, almost never used. So the kind of indexes, you have a couple choices. The kinds of indexes that Firestore will suggest to you. So what happens when you try to do a query with Cloud Firestore the first time is it will fail and it will throw an exception. And in the text of that exception, it will say, hey, you need an index, and here's a URL you can click that will create that index for you. And if you click that URL, it's pretty slick. It'll log you in, and then it'll show you a little box that says this is the index I'm going to create, and you hit OK, and it creates it. It will suggest a composite index that has a single index that covers that entire query. So whatever fields you filtered on or sorted on or selected on will be expressed in that composite index. So it'll be a multi-field index. And I'm giving an example here that's sort of similar to kind of the things that we do. So let's say we have a group identifier. Within groups, we have channels. So there's a channel identifier. There's messages in those channels. So you have a posting person ID, and then you want to sort those by created at. So we have one composite index. So I can do a search on all those fields at the same time to get those results. And with composite indexes, it supports using any combination of the fields, assuming you follow the two rules. First is you have to start from the left, and secondly, you can't skip any fields. So I give an example of the 4 different ways that you could use that filter. So you could do all 4 fields. You could do the first 3, the first 2, or the first 1. This is pretty much the same way that SQL indexes work. So you can sort of start left to right. But you can't skip any fields, and you can't start anywhere other than the far left. So you couldn't, for example, do group ID and posting person ID or posting person and created at with that particular composite index. So the composite index is good for that full search and for sub searches from the left, using those keys from the left. Another thing to understand is that Firestore does what they call index merging. And so it will create a virtual composite index out of individual indexes on smaller sets of fields. So for example, to do the equivalent of what we did with that last composite index, let's say we made 3 separate indexes, with each of those 3 fields, in each one of them having a secondary field of the created at descending. So if I have this, I can now do a search on any combination of those 3 fields, and optionally on either a range select or a sort on the created at. And Firestore will figure out how to combine those 3 indexes into a virtual composite index and run that search. So that's pretty nice. It's pretty flexible. So to be able to, and this may be a little bit of a quirk of our application, that we have a lot of these kinds of searches where there are different sets of fields that you might search on depending on the context. You're not always searching on exactly these 4 fields, every time. But to do that, every permutation of those 3 fields would require 6 different composite indexes to support all those. Or you can do 3 single field, plus sort, and it will merge those together for you. So you end up with, assuming you need all that flexibility, it's significantly fewer indexes, faster performance, and less to manage to build these single field plus sort indexes and have it do index merging for you. So I would argue, in our case, we never use composite indexes. There might be a case where you say, look, I'm only going to search on exactly this set in exactly this order, and that will never change. Then the composite index might be simpler. It's less indexes to manage if that's the case. But if you want any flexibility in terms of which fields you do and don't use in those indexes, like in my experience, it's much better to do these the simple single field plus sort indexes and let Firestore merge them for you. It just gives you way more flexibility, and it's just as fast. So let's talk about query limitations. This is a page right out of the Firestore docs. So it's this page, which hopefully, if you're contemplating using this database, you will read this whole page, and particularly this section of this page. And I wish I'd read it a little bit closer. So let's just go through it. So first of all, Cloud Firestore provides support for logical OR queries through the OR in or array contains any operators. And these queries are limited to 30 disjunctions based on the query's disjunctive normal form. So unless you are a database expert and particularly know about Firestore, you probably don't understand exactly what that means. They give some examples in the documentation. I'm going to give you like a very practical example from our application right after this. But this can be a pretty significant limiting factor if you do need to search on large numbers of values. I'll talk about that in a second. You can use at most one array contains clause per disjunction, basically per field that you're filtering on. This doesn't really end up being much of a limitation because you can kind of code around this. You're not going to be like hemmed in by something you can or can't do with the database. You're just going to have to think about how you form these array contains clauses to make it work. You can't combine a not in with an in, array contains any, or in the same query. It's generally pretty bad at doing negations and even range queries for that matter. So we had an example for one example where we have a query that gets a bunch of notifications, like event log notifications, and we wanted to filter out the ones that were generated by the user themselves. So we didn't want like self notifications. And there turned out to be no way to do that in the query language. We had to just filter it out on the client side. And luckily, that's generally a small percentage of the total notifications. So filtering out on the client side wasn't a huge deal, although it was, made the code a lot more complicated. But negations are a problem. And particularly this next one, only a single not in or not equal is allowed per query. And it's actually worse than that because really this is any inequality. So any not in or not equal or any range query, there's only one allowed. So if you think about things like, I want to see all the restaurant reviews for the last 30 days for every restaurant that has an average star rating above 3. You can't do that because you can't combine the date within the last 30 days and the star rating greater than or equal to 3 in the same query. You can only have one inequality, and that inequality has to be supported by a sort index. So if you want to sort by, for example, date, you have to have that as part of your index, but you also have to have that as part of your index if you want to filter by date, by an inequality, if you want to say greater than 30 days ago or something like that. So this is something that can be a pretty big issue, that you want to be able to do more than one inequality or an inequality and a sort. Anything that is an inequality or a sort, you can only have one of those per query. The not in supports 10 values. I don't think that's a huge limitation. Not in barely works as it is, so having it support 10 values isn't really a big deal for us. And then a query with an inequality filter on a field implies ordering by that field and filters for existence of that field. So again, if you're going to say, I only want to see things within the last 30 days, you will also get the records sorted by the date. And that's the case with any inequality. So just something to be aware of. And that wasn't particularly a problem for us. I could make up a case where that was a problem, but for us, that wasn't a big deal. But the big deal is this disjunction limit. So this 30 disjunctions. So what I originally thought was that's the total amount of ORs I can have in one query. And that's not what it means. So you can, that is one limit. You can't have more than 30 ORs in any given filter because that'll exceed the number of disjunctions. And that or means or like, so in or array contains any are all essentially different ways to do an or. What it actually means is that if you take whenever a disjunction appears in a field, the number of disjunctions for the field for all fields are multiplied together to get the total for the query. And so I know that's kind of complicated, but if you think about how it actually works internally, let's say that, well, I'll go through an actual example. But at any rate, this is, to me, this is the biggest limitation. And depending on the way your data is structured, this may or may not be a deal breaker for you. And I'll give you an example of a real world use case that hopefully will make more sense. So we have a bunch of posts in our system, like lots of posts. And those posts are organized into groups. So people post into a group, and users are members of groups. So you might be in a group, a knitting group and a rally car racing group, and lots of different kinds of groups. And each of those groups have posts in them. So in order to get your timeline, I need to get all the messages, probably sorted by date, that are in groups that you are in. So let's say you're in 5 groups. These groups 1, 2, 3, 4, 5. So I can go to my post collection and say I want to get the posts where the group ID is in this set of 5 groups. So that's fine as long as I don't have more than 30 groups. And initially, I sort of thought, well, maybe we'll make this a feature instead of a bug. Maybe we'll just say, like, we're going to keep you focused to a manageable number of groups and a manageable number of people you follow and a manageable number of hashtags you follow. But that number would be 30. So 30 is the most things that you can do an OR query on in a single group. So that might be a limitation for you already. In our case, it is. I mean, people could certainly be members of more than 30 groups, and already you're broken before you've even gotten into the tricky part of this. So let's look at the real place that it breaks. Let's say that I want to see posts for all the people that I follow. So that means for the groups that I'm in, for the posts in those groups that are posted by the people that I follow. So let's say I want to say where the group ID of a post is in one of those 5 groups, and the posting person is one of those 7 people. That's the set I want to get back. That's going to fail the 30 disjunctions limit because you multiply those together. And this is where it's a little tricky to think about, but if you think about the way the indexes actually work, the way the segmentation works internally, what it's going to do is it's going to, for each one of those 5 groups in the primary index, it's going to build a little bucket of posts. So you're going to have 5 buckets of posts that are all the posts that are, for the group 1, the group 2, the group 3. And then when it has to go do that secondary query, it's going to take each of those 5 buckets and it's going to make 7 little buckets underneath each one of those those buckets for the subset of those that are in the person's match. So you have 35 buckets now. And if you continue to do that, it continues to compound. It makes like a binary tree, basically, or not a binary tree. It makes a tree. So you can sort of see why it's hard based on this index-only access to do these things. But it is hard for the database, and that's why they put this 30 disjunction limit. And I mean, there's no limit to how many they could actually do, but it stops being performant and efficient when you have to do all these disjunctions. They probably prefer. The limit used to be 10, and people complained, and they made it 30. But it has a cost implication, not for the customer, but for Google to operate it, and a performance implication. So that's why they put that 30 limit on there. But this to us was a legitimate practical use case that was not going to work. And even if it wasn't this multiplication factor, it would still have been a problem because you could still follow more than 30 people or be in more than 30 groups. And even without the multiplication problem, you still would have been in a tight spot. So we knew this was going to be a problem pretty early on, and we had a kind of a workaround for it, which I'll talk about in a minute. But this is definitely something to think about. This to me is the biggest limitation of the database, because you sort of say, look, there's no search, there's no table scanning, but at least you have all this index stuff that you can use in these very flexible ways. But even that is pretty limited in how you can use it. So some other Cloud Firestore limitations: there are no joins, obviously. So if you want to filter a document collection by a field or by any data, that data has to be in the document collection that you're filtering. It has to be a top level field. So it can be in an array, it can be in an array of objects, but it has to basically be in that document. And I'll give a sort of example of what I mean by that. There's also no full text search or really any kind of search. There's no table scan. There's nothing like that. You could sort of use vector indexes to do full text search, but it doesn't exactly work, and it's a little bit broken. I'll talk about that in a minute. And also batch writes are limited to 500 documents or 500 operations, which for normal sort of interactive stuff is fine, but it means any of your bulk ops are not going to be able to be done in batch. So if you want to do things like import a bunch of data, or even something, let's say I wanted to some user request that I delete their account, and I have to delete their account, which is all their posts, comments, reactions, everything they've done. That could easily be more than 500 documents. And I can't do that in a batch or a transaction in Cloud Firestore, which is sort of annoying. So let's talk about how the Firestore vector indexes work, because that was one of the things that we were excited about, and we actually did deploy it and use it. So Firestore provides vector indexes. and they're supported as the last field in a composite index. So you can essentially, you can see on this slide how that works. But it'll allow you to search results and return documents in vector distance order. So as it sort of works like a sort criteria. And you can choose your distance algorithm at runtime. So the way you do it is you build a composite index like you normally would. So I have this one on group ID, source domain, source type, and then the final field in the composite index will be your embeddings field, your vector field, and you'll use this vector config, give it the dimensions, and you can give it some other parameters. So essentially now I have an index that I can use to do a query that will query how close these embeddings are to a provided embedding. So great. So that's super useful for like RAG, LLM implementations, other kinds of like sort of, semantic text search. The problems with it that we found, first of all, it doesn't support index merging. This isn't really explained anywhere in the vector and the way the vector indexes work, but through trial and error, we've determined that this is how it works. So if you make, even if you make all of the indexes for the individual fields and you combine them with the embeddings index, just like you would for like a date sort, it will not merge those together. So you can only use composite indexes with vector indexes. You can't take advantage of index merging. It also breaks the partial use of a composite index, which sort of makes sense because you're going to have some series of fields in a composite index, and the last one is going to be your embeddings or your vector index. And since you're going to use that one, you have to use all of the fields that come before it. So you can't like if I have and I don't know why, but for some reason if I have field 1, field 2, field 3, and then embeddings, I can't use that. I can't skip any fields, obviously, and I can't even use the beginnings of those like I would in a normal composite index. So it only works with exactly composite indexes where you're using the exact set of fields in the index every time, which is a problem for us. And it doesn't allow any inequality filters, so there's no pre or post filtering of the vector responses at all. And particularly this inequality filter is kind of a big one. So that means you can't do things like date range. So you can't do things like say, I want to see all the documents like this within the last 30 days, or that also are, I want to see all the restaurant reviews that mention this semantic term where the rating is above 3. So no inequalities combined with that. No real post or pre-filtering period. Like you're just going to get the documents back based on the fields in that composite index. And for us, that was problematic. So because you can only use those exact fully referenced composite indexes, that means for every set of fields, for every permutation or combination of fields that you would want to use with the vector index to do your pre-filtering, you have to have a separate composite index. And in our case, the actual use case we had was we had 4 different fields to search posts that we use in any combination, along with the 5th field being the vector index. So to do the pre-filtering, to be able to do any of those, we would have to build 15 separate indexes, full composite indexes for every permutation of those fields. Each one of those would have a copy of the embeddings in it, which are 768 embeddings times 4 bytes each, so like 3K of embeddings. So it means that if we built all those indexes in order to be able to use this flexibly, like we would do with like a normal merged index, we would have 15 indexes, which means every document write would be 16 writes. It would store 180K of embeddings per 200 characters of text. It would just be it would be insane. It would be crazy. And with some limitations and like pulling back, so if we didn't support this in the app, we kind of pulled back that. We can get down to 4 indexes, but that just did not smell good because it just felt like if we need to do anything, we need to add anything to this, we're just going to be back into that exponential indexes problem, and it's not good. And we can't really post filter on the client because these filters are highly selective, which means we'd have to get back just like tons and tons of records by vector index sort in order to filter out the ones that actually met the criteria that we wanted, and that's not practical either. So because there's no ability to do this on the server side, there's no sort of table scan or post filter, and because of the limitations on the pre-filtering with these fully specified composite indexes, it just wasn't going to work for our use case. There was no way we could think of to make it work other than to just really, really hamstring the app itself, which didn't seem like a good option. So let's talk about some other observations about Firestore. You are going to have index sprawl. You're going to have a lot of indexes. They're not easy to manage. There aren't good tools for it. There's no way to like export and import your indexes in code. There's no like equivalent of like DDL like there would be in a SQL database where you can say like, here's the code that will build all the indexes I need for this set of documents. It's just kind of a hassle. It is sort of nice that it'll give you the error with the URL you can click on to generate the index you need. But as I said, we never use those composite indexes. So my recommendation would be figure out early on how to create the indexes from code. Don't do that from the UX, and have a workflow that builds all your indexes from code. So we basically have a TypeScript script file that calls the admin APIs and just creates all the indexes when we create the new database. And I would recommend doing that sooner than later, so you can sort of manage those indexes, because it's going to be unmanageable if you don't do it that way. If you have to do it through the UX, it's just going to be a beast for anything remotely complicated. So you're going to have a lot of denormalization and a lot of duplication of data in Firestore just because of the nature of it, which is fine. I mean, you get used to it and it's not a big deal. I didn't really hate it. Like, there's a little bit of the old school database, architect in me that bristles at denormalization, but it's not a big deal. So you're going to do that with any NoSQL database. So I don't think that's a unique disadvantage. And then the fact that it's totally schemaless sort of has advantages and disadvantages. For early on in an app where you're just like freestyling and adding stuff and going nuts, like, yeah, it's awesome not to have to worry about that. But I think there's a point at which having a schema and understanding the ability to do migrations and sort of understand the shape of the data and in a reliable way all the time, and know that every record in a collection is going to comply to the same shape is useful. So I sort of feel like for starting out, no schema is great. And then at some point, like, I'd just rather have schema. So I'll say the max disjunctions was really the limiting factor, and the thing that caused us to think hard about switching. And we weren't originally going to switch. Our original plan was we were going to add Elasticsearch, and we were going to use Elasticsearch to do all the searching that we needed to do that broke the max disjunctions limit. So for the bulk of like the display, computing and displaying the timeline, we would just use Elasticsearch for that, which would work fine. So we started playing with that. Elasticsearch is also sort of a bear to set up and manage, and it's like one of these air quotes fully managed services that is not really fully managed, but that's you still have to be somewhat of an Elasticsearch expert. But we're looking at that. It's like, okay, great. So we can synchronize that, and then we can build indexes in Elasticsearch, and we can also store other data besides the indexes, so that when we do a search in Elasticsearch, we can actually get back all the data we need to display the timeline. So we don't even have to go back to the database to Firestore to read the data. So it sort of seemed somewhat workable, but a little bit scary. And looking at that, I started thinking, well, why don't we look at Spanner and see? I think Spanner can sort of do the same. Spanner has a good vector search, also has some other facilities, has text search. So why don't we just look at using Spanner instead of Elasticsearch, because it might be a little bit easier to manage. And then going down that path, it's sort of like, well, if we're going to use Spanner for that search, why don't we just use Spanner for the database? Like, why have two databases? Why don't we just put it all in Spanner? So that was a little bit of the genesis that started the original spike that caused us to use Spanner. And then once we started doing that, we were like, yeah, okay, great. We don't need Elasticsearch, and Spanner is a much better fit than Firestore was. The other issue was just the vector search on Firestore wasn't usable for our use case, which is the thing I just talked about. So having to have all those composite duplicate indexes and storing all that data, there just wasn't a good workaround for that. I think with any of these vector databases, and I'll talk a little bit about this in Spanner as well, the pre and post filtering is the hard part. Like, doing the vector search is not the hard part in particular. It's the other part of it that's sort of the hard part. And neither one of the databases does great at it, but yeah, in the case of Cloud Firestore, it just wasn't going to be workable. So we would have had to, again, go out to a third party. We'd have had to use Elasticsearch or a true vector database to do the indexing, to do the vector searching, which wouldn't have been great. So Spanner to the rescue, sort of. And I'll talk about this sort of. So let's talk about Spanner. So Google says it's an always-on database with virtually unlimited scale, and it's fully managed, mission-critical relational database service. Sort of is. It's sort of SQL as a service. I would say when they say fully managed, they have a definition of that I don't disagree with. But it's not zero ops. It's not like Cloud Firestore. It's not like S3. Like you're responsible for capacity management. They have auto scaling and preview, which means like even though this service has been around for years, they still haven't really figured out auto scaling to the point that it's actually a GA feature. So you're going to be responsible for managing capacity, which doesn't mean just turning the knob, but it also means like watching the logs and watching the usage and assessing how much capacity you need and changing it. Like you're going to be spinning that plate. You're responsible for understanding the region distribution of your solution, which is not a bad thing, but it's just something else you have to do, whether you want it to be single, dual, multi-region, if you want read-only replicas, where you want them. You're going to have to manage backup and restore on your own, replication management on your own. You're going to have to monitor all that stuff. And it's SQL, so you get all the fun of operating SQL at scale, which means you're going to have to deal with index management. You're going to have to constantly be looking at query performance and transaction performance and optimizations and lock contention and all those things to figure out how to either modify the database or indexes or the way you're using it in order to make it performant. So there's some overhead with that. It is not just like turn it on, configure it, and go, and you have a database, and it's it works great. Which Cloud Firestore, in its defense, is that. The pricing model for Spanner is also not super startup friendly. They have a free tier, but it's time limited. I think it's only for like 90 days. So it's just sort of a try it before you buy it. But they don't really have anything to support like I'm solopreneur and I want to run some app at a very small scale. You pay based on compute capacity, not on usage, but capacity of compute and capacity of storage is the primary lever. There's also a slight amount of you pay per storage used, but it's pretty competitive. And there's a bunch of add-ons that for replication and compute boost and like a whole bunch of other things. There's also 3 different editions. This is fairly recent, but like levels of support and features that are all at different prices. So they're kind of a multiplier on the base price, not a huge amount, but like 15 and 30% or something like that. But the bottom line is the minimum instance cost is for the smallest instance you can run is $75 a month, which, again, that's not a lot of money. That's 100 units, which is a tenth of a node. So one node would basically be 3 servers, three dedicated servers. So if you were going to run this at any kind of real scale for any real business, one node is the least you should run, because then if you're running less than one node, if you're running in units, you're running on shared infrastructure. So you can't even really be guaranteed that the performance is going to be consistent over time. They sort of let tenants float around a little bit. So anyway, you're looking at for a real application deployed to paying users or an enterprise app to pay, to look at one node being $800 a month, not a giant deal, but it's not the, very competitive pricing you'd have at small scale on Firestore. So you're going to have a higher cost to stand it up, higher cost for a minimal instance, and you're going to be capacity pricing versus usage. So at any scale, you're going to have a higher fixed cost relative to other kinds of pure usage-based solutions. It's going to require you more expertise to stand it up and configure it and optimize it. And if you have a strong SQL background, that's not a huge limiting factor. But if you didn't have a strong SQL background or somebody in your team with a strong SQL background, I would be reluctant, I think, to pick Spanner. But I guess that's sort of obvious. Don't pick up SQL database if you don't have some SQL skills. But you could do that with Cloud Firestore. You don't need to have any Cloud Firestore or NoSQL expertise to make that work well. Whereas on the SQL side, you kind of do. And so there's the point I made in bold is, you're going to be investing time with SQL expertise to operate and optimize and tune this thing in order to keep it healthy and functional and performing over time. And even if that was a tenth of an FTE, which it was very conservative, it's probably more like 1 FTE at any kind of scale. You're talking about, tens of thousands of dollars are going to be added in soft cost to run Spanner. It's not going to be free. And it might be worth it. In our case, I think it is worth it, but that's just something to consider. There is some plate spinning and some specific SQL expertise required to make this work well, in my opinion. But it's SQL. I mean, you don't get to be the predominant database implementation paradigm for 50 years for essentially all of modern computing unless you're doing something right. And the fact that they haven't really had to evolve it very much to make it work with the things that we're using it for now is pretty amazing. So you get the power and flexibility of SQL, which is awesome. It's super high performance and really good tooling. And by power and flexibility, I mean no limits. You can do anything you can do with data. It may not be super fast without some tuning and some thinking about it, but it's not going to tell you no ever. So the tooling, the Spanner Studio, I really like. I think it's the Firestore Studio is pretty decent too, but I think the Spanner Studio is very nice. You get a lot of not only the ability to manage your instance and all the tables and indexes and everything, but also telemetry analytics. You get a nice SQL interface. It's got some advanced analytics, which are not just timing, but also sort of detailed analysis of queries and transactions. And you can look at those even if you don't do any tagging. You can actually still go through and see these. They group the transactions and the queries together, so you can see when there are sort of repeated patterns. You can go in and kind of debug them. But if you do want to use tagging, so in code, you can apply a tag in your SQL through the toolkits to a given query or a given transaction, and then it will group it using that tag. So that can be super useful if you have some particular problem area or something that you're concerned about, and you want to see on the back end what's going on, how fast those things are performing, what kind of data is being passed in and they're returning with those particular queries. It's pretty nice. It's a really nice environment. I'm a sort of a sucker for like good interactive GUIs. And they have tons of capacity metrics, lots of interesting stuff that show you all, your lock contention and your CPU usage and just a million other things. So again, it's a two-edged sword, because having 100 knobs to turn and 100 graphs that show you how things are going is awesome, but that also means somebody's got to turn those knobs and understand what those graphs all mean. Like, you don't have to do that on Firestore, but you do have to do it on Spanner. And it's got really good, well-supported client libraries, code samples. It's a pretty developer-friendly database, particularly for a Node.js developer. So that's it. We're using Spanner via Node.js. We're using the Google-provided open-source Node.js client. I'd say it's relatively well curated. I tend to assess these by looking at the ratio, the number of open issues and PRs, the ratio of open to closed. I try to look at issues like how old are the oldest issues, and are they like real issues that somebody should be on top of? And the same thing with PRs. Are there open PRs that look like they're solving real problems, that look like they meet the criteria, that are just sitting around? So that's sort of how I assess, is this thing actively curated? And I would say I feel like this is. I think they're pretty on top of it. Who knows if that will keep happening, but right now it seems like it's pretty well supported. The TypeScript support is pretty good. I'm a little bit of an oddball in that I use TypeScript. I'm not sure I'm happy with that decision, but I have too much TypeScript to turn around now. So, but the TypeScript support is pretty solid. Most of the implementation itself is in TypeScript. So when you're looking at the source code, which you will probably have to do periodically, it's in TypeScript. And there's lots of code samples of the Node.js client. So everywhere in the Spanner docs, there's a little multi-tab control, and you can click Node.js and you'll see samples, and it'll all be using that library. So it's pretty easy to translate that into the code you're working on. Let's talk about connection pooling. So they don't really explain in the Node.js library how connection pooling works. They explain that it exists and that it works and it's magic. They also in the Spanner docs tell you that creating sessions is expensive, but they don't really explain how to use the session pool. And I originally implemented the database in a way that I was not using the session pool, and I found out sort of the hard way how bad that is. So when they say creating a session is expensive, it's not like a little bit expensive. It's like ridiculously expensive. It's hundreds of milliseconds inside the Google infrastructure, and outside the Google infrastructure, it's like many hundreds of milliseconds to create a session. So we'd see things like doing a transaction would be like 800 milliseconds, and then with the session pool, the second one would be like 75 milliseconds from a remote source, and internally like way faster. So you have to this is not usable without session pooling. Just like with the way that Gripsy works underneath. And the way those libraries work, and the way they build those sort of, multi-channel sessions, like you have to use session pooling. So the way you use session pooling, which I would love to see these two sentences added to the doc somewhere. They're managed by the Spanner database object. So there's a bunch of objects. You get like an instance, and then you get a database, and then you get like transactions and this whole tier. They don't really sort of explain what these things do and which ones are lightweight and which ones are heavyweight. So the Spanner database is a heavyweight object. And in order to take advantage of session pooling, you want to have that be shared and long-lived. So you basically want to create one Spanner database object, and anybody who needs to access the database should access it through that object. And by doing so, they will be able to take advantage of session pooling. It's pretty straightforward, not explained anywhere. It took a fair amount of trial and error and reading the source code to figure out that was the case. And part of it is because a lot of the code examples were, they would get a database, open it, do something, and close it. And if you do that, and you open and close the database every time, you're not using session pooling, if you sort of follow the examples. And if that's your whole app, if your whole app is just opening a database and doing one thing and closing it, fine. But if you're writing a real app, you're going to be sharing that database connection. So anyway, just important safety tip. The other important safety tip is, if you are sharing these Spanner database objects and you have more than one of them open against the same database in the same process space, and you close one, you will corrupt the session pool for any remaining open ones, and it'll throw a whole bunch of session leak exceptions. So that was another problem that I ran into when I wasn't, when I didn't have this implemented as a singleton. So hopefully that'll be a helpful safety tip. It'll save somebody like 8 hours of debugging if they run into this. So we'll talk about a little bit of the tooling we did. There's a lot of like boilerplate copy and paste code when you're using Spanner to get the database, to do exception handling for what happens if you getting the database fails. And then when you get into the database and you're doing database operations, to be able to trap those exceptions. And it gets even worse with transactions. And you end up with like either just the nastiest callback hell stacks, or like at the very least, you end up with like multiple contained try-catch blocks. So we wanted to avoid that after like doing enough of these to see that pattern was going to be painful to maintain. So we did two things. We built this with database wrapper. So this is a generic typed wrapper. And what it does is it gets the database for you. You don't have to worry about the details of how it gets the database. and it provides, and you give it a function that takes a database as a parameter. So it essentially gets the database and passes it to your function. And then it handles any exceptions that are thrown and then passes back the result. So you say await with database, you pass it your user, which is what it needs to get the tenant, to get the database, and then you pass it an async function that takes the database as a parameter. So you just get a callback, that passes the database that you can go to town on. We did a similar thing with transactions. So you call with transaction where you pass it the database, and then you give it a function that takes a transaction as a parameter, also generic typed, which means if I return a value from that contained function, that will be returned from the top level function. So it'll sort of bubble through. And so what that looks like is I'll say await with transaction, database, and then a function that takes a transaction, and then I'll do stuff with the transactions. So the nice thing about this is it handles catching any escaped exceptions. It handles rollback and commit automatically. And there's some sort of complex logic around retry and around what happens if you catch an exception during the commit versus during the actual operation of the function. And all that's handled with transaction. So the bottom line is it means all of our database code looks sort of like this. You do an await with database, and inside of that, if you're doing a transaction, you do an await with transaction, and then you just do your transaction stuff, and that's it, and you exit. And as you exit that function, if you haven't thrown any exceptions, that transaction will be committed. Any kind of cleanup will be done for you automatically. So this makes the code a lot cleaner and more readable. The other thing it allowed us to do is if I ever need to instrument what's going on with transactions or with databases, I can instrument it in the wrapper functions, which is pretty nice. If I need to change the behavior of any of the retry behavior or exception handling behavior, which I've had to do a couple times, I'm able to do that with these wrappers. So pretty nice. I feel like a good way to handle that. So let's talk about transactions. With Spanner, transactions fail all the time, lots of the time. And looking through, Googling and finding people complaining about the kinds of failures that I'm seeing. I've saw lots of stuff on Reddit and Stack Overflow and lots of places, people complaining about the same exact kinds of errors that I've seen. And the general responses from Google have always sort of been like, A, it's probably your fault, and B, like, don't worry about it. So there's this really definitive document that lists like, here's like the 50 reasons a transaction can fail. And like 49 of them are under this contention bullet, which is things like multiple transactions trying to modify the same data concurrently. And then there's this one thing, which is transient errors, temporary internal spanner conditions, or network glitches. That's the catch-all. In my case, it's 100% that. Like I have this code that we use in our CI/CD that builds a database from scratch, populates it from mock data, and then runs a bunch of unit tests in it. And when I run that to populate the mock data into that database is about 60 transactions, and it fails. At least one of those transactions fails every time I run it. So that's how frequently it fails. Sometimes a couple will fail. Every once in a while you'll skate through and none of them will fail. But generally speaking, you're going to, even on just 60 transactions, and that's a single threaded application that's running the exact same code in the exact same sequence with no data contention, no table contention, nothing. So that should never fail. And when those transactions fail and they retry, they always succeed, which sort of implies that wasn't really my fault to begin with. So what I will say is transactions are going to fail. And in my experience, they always succeed when retried, and you just have to decide you're okay with that. Which means you have to have a retry mechanism around your transactions, which is that, frankly, that is the guidance that they give you. Initially, when I wrote it, I was like, look, I want to see all the failures. I want them to blow out and kill the app so I can see what's going on when they fail, so I can understand when they fail and if it's my fault. And after a while, I kind of got to like, okay, it's not my fault. So we're just going to do the retry. So we use the run transaction async inside of our with transaction wrapper. We use run transaction async, which will call your callback function. And if your callback function throws an exception that's retryable, it will retry it a few times. And it's got some code to deal with kind of the intervals at which it retries and how many times it retries and that sort of thing. Another thing, just to if you're watching that, which you probably will be at the beginning, sometimes those transactions will retry by just calling your callback again and running the whole thing again. Sometimes those transactions will retry and succeed without calling your code again. So if there's enough state in the transaction itself, if all it has is pending mutations and it has enough state in the transaction that it doesn't need you to run it again, it can sometimes recover without it. So you will not necessarily see your callback called again in a case where a transaction fails and is retried. You might or you might not. So just hopefully to give you a little bit of grounding of what to expect with transactions, because you're going to use them a lot in Spanner. There's also some issues with Spanner and Next.js and Webpack. So if you're using Next.js or anything that does Webpack, there's a couple of issues that I think are sort of broken in Spanner that I was able to work around with. But what happens with Spanner and some other Google libraries that use the GAX library to talk GRPC, if you don't know what these acronyms are, don't worry about it. But the grpc requires proto files to be loaded from the npm module at runtime, and that's not something that the Webpack environments necessarily know about. So those modules aren't available to it. So you have to do a little bit of work to stage them properly. And then Spanner has a particular oddity where it uses this require.resolve to locate the protofile directories, which fails in a Webpack environment in a way that there's not really a workaround for. So I came up with a workaround to both of those. I opened an issue, this 2137, on the GitHub repo. So if you have this particular problem, just go look at that issue. I assume they're going to close it, not fix it, but I just put it in there with all the details of the workaround. So if anybody else ran into that problem, they wouldn't have to get stuck like I did for 12 hours, trial and error sorting it out. So let's talk about some key differences. So indexing is one of the big differences. So Firestore, as I said, you have to have an index for every aspect of record access, every query condition, every inequality, every sort, everything that you do that provides access to data is through an index and only through an index. With Spanner, as a SQL database, you can use indexes for optimized access, but you don't have to. So it can do table scans, and it can be very fast sometimes. And depending on the selectivity of the query condition, sometimes you don't need an index. But you always have that ability to build indexes and tune them to make query performance better. And it gives you really good tools to do that, to optimize and understand how queries are working and whether you fix them or not. Transactions. So Cloud Firestore supports transactions, but sort of. I mean, you read the documentation, it's not going to make you excited to use transactions. And in our case, we were able to implement a pretty complete, I would say, complicated application with transactional integrity without actually using transactions in Firestore. And the way that we did that was we used batch writes instead. So batch writes are sort of a separate concept from transactions. With a batch write, the only guarantee is the entire set of writes in the batch will be executed atomically or not. They'll either be all be executed together or none of them will be executed. And the way that you can solve the transaction problem, at least for us, is that within those batch writes are these field level atomic updates that you can do. So you can do things like say, I want to increment this field by 1 or by 7 or decrement it by 3, or I want to add or remove an item from an array element, or I want to write a time to a time field from the batch write time. So there are all these things like tricks that you can do. And what they allow you to do generally is avoid the reason you would need a transaction, which is a sort of the read increment write problem, right? So if you're using a transaction to increment a counter, for example, you have to do a transaction and then do a read so that you know that nobody else is going to be relying on the read value of that transaction while you're modifying it. So you read the value, you increment the value, you write the value and the transaction, and the database manages the access of that. So if multiple people are trying to do that exact same thing at the same time, you're not going to miss any or have any overlaps. And Firestore can do the same thing with this sort of these batch writes and these field level atomic operations. So in our case, we never actually needed a transaction. We were always able to do it with this combination of batch writes and field level updates within the batches. In Spanner, virtually every write operation you do is going to require a transaction. So literally everything you do, you're either going to be writing to multiple tables, which in our case we almost always do, because even if we're doing a simple operation, we're writing a log record at the same time. So you're always going to be writing to multiple tables, and so if you want to commit those, atomically, you're going to need a transaction. And if you do any kind of read first write, and in our case, a lot of the read first write is just like read to see if the record exists or not, to know if you're doing an insert or an update. So even that requires a transaction. So just get really used to the fact that like you're going to use transactions for really every write operation for the most part, and it's fine. Like Spanner is optimized to support that use case. Kind of unlike Firestore, you shouldn't feel bad about using transactions because you're going to use them all the time. Normalization is the other big thing. So often Firestore requires you to denormalize your data, and Spanner actively prevents you from denormalizing your data and requires you to normalize it. But I'll give you an example to try to explain what I mean by that. So let's say we have posts in our social media app, and those posts have reactions on them. In Firestore, if we want to let's say we want to get all the posts which were reacted to by a certain person, because the thing we want to get back is a post, that means we have to search the post collection, which means the fields that we're filtering on have to be fields that are in the post. So they can't be fields that are like in another collection or another relation or another table. They have to be in the post. So in Firestore, what we have to do is we have to store an array of reacting person IDs, and we actually store an array of reaction objects in the post so that they're in that post collection, so that we can filter the post collection based on the reacting person ID. So it's forced denormalization. If you want to select or filter posts by reacting person IDs, they have to be in the data. They have to be in that record. And in Spanner, it's sort of the opposite. So the reason that works is because when you create indexes on Firestore, those indexes can be indexes into multi-value array fields. So I can build an index on a reacting person IDs, this array of reacting person IDs, and I can use that index to get post records that have IDs that match that, so one or more. So with Spanner, you don't have the ability to do an index on an array field value. So that means you have to normalize the data. So you have to make a post reaction table that relates to the post table through the post ID. And then you can make an index on the reacting person ID in the post reaction table, and you can do a join. So this is like a very traditional SQL operation. But I guess the point I'm trying to make there is that the database model forces you into how you normalize or denormalize the data. Like, you don't have a choice. Like, this is how you do it in Firestore and how you do it in Spanner, and there's not really any other way around that. So just something to think about. So let's talk about how we did the port. So the first thing we did was we built a model abstraction. We built a set of abstract-based model classes. We already had, like, I made a models director with a Firestore directory under it, like on the theory that maybe there'd be another model someday, even though I'd never planned on there being another model. But I didn't build an abstraction layer in between. So we built this abstraction layer, and then we built a Firestore-specific version of that extended that, and then we built a Spanner, sort of an empty Spanner skeleton that implemented the same interface. And then we created a factory pattern of class getters to access the model implementation. So now instead of saying like, hey, I want to go get this person model, you call the factory and say, give me a person class instance, and then it'll give you whichever one is being used actively. So you're at the API level, you're completely abstracted from whether it's Firestore or Spanner. And so probably the best way to talk about that is like what the code looked like. So what the code used to look like is you'd import this person model from the Firestore person model implementation, and then you just call your methods on it. The way it works now is you import this getPerson class function from the model factory. You call the getPerson class to get the person class. So this is not an instance of the person model. This is this is the class of the person model, and then you can use that like you would have used the class that you imported directly. So we're basically adding this sort of getter to get the class and then operating directly on that class, just exactly like we would have before. So the code changes were pretty simple. Like, we didn't have to make a ton of changes. We just had to implement. We had to just replace the imports and add the factory getter to get the classes. But the actual usage of the class code didn't have to change. So when we created the abstractions, we found some leaks that we had to plug. I don't want to get like too much into the weeds on this, but essentially with TypeScript, and you might have this with other environments. So we had a Firestore model implementation, and we're trying to present an abstract, sort of like a generic, not Firestore specific interface to our API clients that we're calling the models. But the models also called each other. And when the models called each other, they had to understand in some cases some implementation and details of the database that they were in. So I'll give you an example. Like when you write a post, the post creates an action record, which is sort of like an audit log record, and it wants to create it inside of the same transaction that the post action is happening in. So the action record interface, which is also exposed to the API level, has a mode of use where you can pass it a transaction. And that's fine. That should work that way. But there's really no way within the type system to prevent the caller from up above from knowing about the fact that this sort of lateral call exists. So if you had if you had namespaces or a package convention, if you had some other kind of like type system, you might be able to do that to say like everything in this module scope can access these protected functions or whatever. But in TypeScript that doesn't exist. So it's either public or it's not, or public protector or not. So we ended up with some of these things kind of leaking out. And so what I would say is the lesson learned from that was I should have built an abstract layer in between, like an abstract class layer in between, so that I could solve that exact problem of saying like it's okay for the model to know about the implementation details of their sister classes and then be able to guarantee that I have a strict contract above that where nobody calling that knows anything about Firebase or Spanner or anything else. So anyway, keep your model contracts clean and abstract. And find a way to enforce it. If you're using Node.js, something like this works. If you're not, you might have other mechanisms to do that, like namespaces. So the other thing is when we implemented Spanner, it would have been nice to have this be totally plug and play where no client code had to change, but we did have some issues. So we had things like we would denormalize a field into a record, and then we'd have a getter that would get the results. So like, let's say for that reacting person ID, for example. So I could just have a getter that would get me the reaction person IDs. That's a synchronous getter function. Well, now those are stored in another table and I have to do a lookup. So now that's an async function. So we had a few cases where we had to take these property getters for denormalized data and we had to turn them into async accessors. So like a get async function to go get those things. Not a bunch, but half a dozen of those. We had a few APIs that we found were returning the model objects directly over the wire, which was bad, that we didn't realize was the case, but found out that was the case. So we had to update those to return typed payloads. And then the other thing is with Spanner, so Firestore is really good at paging because of the way their index retrieval works and sort of building this big record of, or this big sort of list of index results. It's very easy to tell it like, hey, replay that same query, but start here this time at this ID. In a SQL database, you don't have that. You're going to implement the paging yourself. So what we had to do was essentially say, we're going to do it by date, and then we're going to use the record ID as the tiebreaker to do paging. So now all these APIs that used to require in their cursor just the record ID now require the record ID and the date. So not a ton. Like this is actually a pretty small amount of code. And the big PR. So we have 264 integration tests, and essentially when I first started working on this, 5 of them passed, and then 7, and then 10, and then eventually after 3 weeks, all of them passed. And we're able to look at the code coverage. And it was a pretty big change list. I've talked to some of my friends about how you would have gotten by with a change list like this in a real company with lots of developers. And so this is a 3-week long change list that had 13,000 additions, 3,300 deletions. Those were mostly things that got moved. So let's call that 10,000 lines of code changed. So 10,000 lines of code across 142 files, just almost every file in the entire project over 3 weeks. So if that was a real change list and I had to reconcile all the changes that the entire rest of the team had made in 3 weeks, and then somebody had to go look at this PR and say, sure, it looks good to me. I don't know how you would have gotten away with this, but it was a big PR. So about 3 weeks end to end. I think if I had had that abstraction level in between, this probably would have been like 2 weeks. Anyway. So final thoughts, Firestore has a lot going for it. And if it works for you, it might be a great choice. Like I'm not saying don't use Firestore. It's fully zero ops, which is great. It's usage-based pricing, no domain expertise required out of the box. You can build scalable, high performance, highly available solutions. As long as what you're doing is within the limits of what it can do, I think it's a great solution. And a lot of times with a little bit of expertise, you can work around some of those limitations. But the problem is there were times for us where we just couldn't work around them. We just couldn't expose some piece of app functionality or some mode of use through, there was no way to make it work that we could figure out without using another database as a sort of a crutch. So I would say unless you have a very well-defined specific use case and that these limitations are not going to be a problem for you, I would look hard at that. I wish I would have looked harder at it to begin with. On the Spanner side, it is fully managed, which means you're not going to have to manage, database versions and patches and that kind of stuff, but it's still going to require a significant amount of ongoing operational investment. It's going to require SQL domain expertise. Like I would not jump into this not being a SQL expert. But it doesn't have any limits. It can do anything you want it to do. Might not do it out of the box. It might not be super performant without indexes and optimizations, but the answer will never be no from the database. That tooling is really good, I think. I think it's likely this can be more expensive at scale. It's not entirely clear. It's hard to sort of estimate. Like with, I can take a usage-based model, and I can say with this many users doing these kinds of operations this frequently, I can kind of compute what that's going to cost me in Firestore. In Spanner, who knows? Like I don't know how much capacity is required to support what level of support. I don't know how well the auto scaling is going to work, how flexible it's going to be. We're scaling up and down. It's hard to say. The good news is it's SQL, and even though there's a little bit of Spanner dialect to the node library that we're using, it's fundamentally SQL underneath. And if we needed to move to another SQL solution, I think it would be very easy to do. I think that would be like a 1-week port to move to any other SQL implementation. So we could go to Cloud SQL on Google, we could go to Aurora, we could go to any number of other databases if we had to, without having to kind of rewire the brain about how the data actually is laid out, how the tables interrelate to each other, how the model works. So not like a Firestore to Spanner or back is a rewiring your brain and rethinking about how the data relates to each other. Spanner to any other SQL, I think, would be a lot more straightforward. So I'm not super worried about the downsides of Spanner because I don't feel like I'm not as locked in as I would be with something like Firestore because it's SQL. So that's it. Hopefully that has been useful to you if you're thinking about one or both of these databases. If you're starting a new project, if you've gotten part of the way down the road and you're not sure, hopefully some of these insights will be helpful to you. So thanks a lot. Talk to you next time.